Greetings, intellectuals. We continue our discussion. Today we look at 4 aminoquinolone class of drugs. We'll refer to 2022 tutorial sheet, question D. Question A states, elucidate the structure of amodiaquine and clearly show the part of the structure responsible for its limited clinical use. Okay, so our structure of amodiaquine is as depicted. So the key points to note in our structure of amodiaquine are the 2 rings. Okay, so this is our heme binding template, where we have a benzene ring fused with a pyridine ring there. Okay, so these 2 are the aminoquinolane nucleus, and of course we have our amino group, which is the NH atom on the 4th carbon of the ring. So this 4 amino is attached to our linker. Our linker in the case is a benzene or a phenyl group, and we have our terminal amine here. So this is amodiaquine structure. Okay, so on this structure, toxicity can arise. So toxicity is as a result of this structural alert here. Okay, so this hydroxyl here is able to undergo oxidation, and this hydrogen here is able to be lost as a proton. Okay, so oxidation can occur on the hydroxyl there. So upon oxidation by the cytochrome P450 enzymatic cascade, we lose the hydrogen and form a quinonimine derivative, which is a toxic intermediate and has affinity for proteins, causes hepatotoxicity and agranulocytosis. Okay, so it starts fighting the granulocytes and fights the hepatic tissue. So it's quite toxic. So the name of this toxic metabolite is the quinonimine. Yes. So this quinonimine is the reason for amodiaquine's limited use. Okay. B is asking us to bring up why amodiaquine achieves high in parasitic concentrations of the drug. How does it accumulate in the drug, and what structural component enhances the accumulation of amodiaquine in the drug? So amodiaquine has a terminal amine, okay, that is basic. Upon entering the digestive vacuole of the parasite, which is acidic, the basic amine is ionized by ion trapping. Okay, we'll discuss that component, ion trapping. Okay, after ionization, this allows for a pH gradient to be created into the digestive vacuole of the parasite, therefore promoting accumulation into the parasite. So this has been depicted structurally below. We can see amodiaquine here in the uncharged form. So this is in the red blood cells, where the pH is 7.4. Okay, of course, let's note that the terminal amine of amodiaquine is at 8.1. So it's quite basic, or it's quite basic as compared to the internal environment of the parasite, which is at 5.5, the digestive vacuole of the parasite, which is at 5.5. So what happens is, upon diffusion inside the cell from high concentration to low concentration, amodiaquine becomes ionized inside the cell. That means the charged amodiaquine cannot go back outside. It's trapped within the membrane there. Okay, this ionic difference creates a pH gradient. Okay, what we have illustrated with the arrow there is a pH gradient, which is 1000 times more than the accumulation in the red blood cells. So the pH difference really contributes to this increased fold of diffusion into the parasitic membranes. So this is due to the difference in pH. So the highly acidic pH of the digestive vacuole, which is 5.5, allows for the terminal amine to be charged, because the terminal amine will get an extra proton in the acidic environment. Okay, if that occurs, our nitrogen becomes positively charged. So in the acidic environment, there is this charged amodiaquine, and the parasite itself will look at amodiaquine as the uncharged form. The charged form won't be recognized as amodiaquine. So this allows for a continuous flow of amodiaquine into the digestive vacuole because of the pH gradient, which is not being balanced, which keeps on being unstable. So this allows for a continuous flow, okay, until the parasite eventually dies. Yes, which is a quite effective mechanism. It contributes to the effectiveness of these drugs. Okay, we'll see that component in a range of class of drugs, especially anti-malarial drugs, due to the same reason. Okay, so question C wants us to illustrate a brief structure-activity relationship of this class of drugs. Okay, so I'll be pinpointing individual structure locations on the amodiaquine structure above. So first point of the SAR, 4-aminoquinolene nucleus, which is a heme binding moiety. So this 4-aminoquinolene nucleus there is essential for activity. Okay, tertiary amine in side chain. Okay, tertiary amine in side chain is essential for activity. So our tertiary amine, okay, our tertiary amine at this point, which becomes ionized to allow for the accumulation inside the cell, should be and is essential for activity. So it's a very important component. So our terminal amine or tertiary amine is essential for activity. 7-chloro in the quinolone nucleus is important for activity. So 7-chloro is essential part of activity. So the chloro on the 7th carbon is essential for activity. So 1, 2, 3, 4, 5, 6, 7 chloro. This chlorine atom here is essential for activity. So use of any other halogen can be permitted, but optimal activity is derived from chlorine. So chlorine yields optimal activity at the 7-chloro position, therefore is quite essential for activity. So fourth point, the introduction of the alkyl group at carbon 3 will reduce activity. So at 1, 2, 3, introduction of alkyl group, per se ethyl, methyl, or any alkyl chain will lead in reduced activity of these drugs. Okay, so no alkyl substitution should be done to preserve activity. The D isomer of chloroquine is less toxic than the L isomer. Okay, so isomerism is an important aspect of these agents as well. So the D isomers are less toxic than the L isomers. 4-amino can be primary, secondary, but not tertiary to maintain activity. So 4-amino, we resort to our structure. 4-amino is this amine right here. Okay, so we can have a bond from the aminoquinolene nucleus alone, and we can have a secondary bond with the linker as shown with this phenyl group, but we can't have another additional bond on nitrogen. Okay, so we can't replace all the hydrogens on our amine. We are limited to only secondary but not tertiary on this amine right there. So that is a very important point to maintain activity of these drugs. Length of the linker was reduced from 4 carbon to 3 carbon, or addition of a ring or a phenyl to overcome chloroquine resistance. So as we see in amodiaquine, we have added a linker which is a phenyl group. This ring structure has been a strategy to combat chloroquine resistance, because the length of the linker has an implication in resistance. And what we find to say is that reduction of the carbon numbers of the linker, okay, which is the R group between the terminal amine and the 4-aminoquinolone amine. So the length of the linker has an implication in resistance, in that when we reduce from 4 carbons to 3 carbons or 2 carbons, we tend to overcome the resistance of these drugs structurally. Okay, so we can either reduce the carbon numbers or add a phenyl ring or a ring structure as a linker to overcome the resistance. Yes, so that has been a strategy, and it's a very important part of the activity of these drugs. Terminal amine is essential for activity. Of course, as noted, the terminal amine is the one that allows for the drug to accumulate intracellular. It should be very much essential for activity. And the terminal amine allows for accumulation of the drug, okay, in the digestive vacuum, as we have explained. Okay, and then question D, illustrate the mechanism of plasmodium resistance to chloroquine. So the mechanism is primarily attributed to the development of what is known as a Plasmodium falciparum chloroquine resistant transporter. Okay, this transporter becomes coded for and is present on the digestive vacuum membranes, and what this transporter does is it then starts removing chloroquine from its site of action, okay, which is the digestive vacuum within the parasite. So this protein efflux, okay, this process of the Plasmodium falciparum chloroquine resistance transporter removing chloroquine from its site of action is termed as protein efflux. Protein efflux. Okay, so this protein efflux mechanism, okay, allows for concentrations of chloroquine to reduce drastically. This reduces the activity of the drug. So this is the main mechanism behind the resistance of chloroquine. Question E states, outline the strategies that were employed to overcome chloroquine resistance. So as we have implied on amodiaquine here, reduction of the linker length from 4 carbon to 3 carbon or 2 carbons has overcome this problem of resistance. The second strategy is the use of rings as linker fragments, rings such as phenyl rings or heterocyclic rings, as seen in amodiaquine. So amodiaquine can be known as a modification made to improve on chloroquine resistance, because the ring, the phenyl ring on amodiaquine, has been implemented as a strategy and has been seen to overcome this resistance. So chloroquine has activity over chloroquine resistant strains of malaria or Plasmodium falciparum. So such strategies such as reduction of linker length, okay, reduction of linker length from 4 carbon to 2 carbon, and the use of ring as linker fragments has been helpful in chloroquine resistance. Okay, we reach the end of our discussion. Thank you and shalom.